So you should be doing one about a car and a plane, and evaluating a limit, and then finding dy dx. On screen. I drew a little picture off to the side there. In the end, I think it's just a triangle. I think it's a right triangle with the Pythagorean theorem. So look over some of those details there. Hopefully I didn't mess up any of the little numerical values. Okay. 13. What you just said?
We all got it at this table.
Yeah, but
all three of us.
we had the same exact work in. Let's see.
You have the exact same work, except you got 13. So you have the exact same numbers, except for the very last answer?
Yeah.
I sure hope you're right. I hope I messed up. I don't know how I would have, but I'm hoping.
What was your?
It's a Monday morning.
Oh yeah, we don't really.
I'll run the numbers myself too. Let's just see what happens. Should be 2 times 0.07 times 100. So it's 14.
Oh, did you drop the 2 down when you went from that set to that set?
Did I drop the 2 down?
It looks like you forgot the 2, or the 2D.
It would make it 198, but that would make it 20, like 27, 26.
I don't know.
I don't know, let's find out. So
No, it looks like.
that kind of makes sense. So, yeah, so if I, that's really weird. So if it's really strange. Okay, so let's try this. 14 divided by 2 times. Okay, you guys said 13, but you probably meant 13 point something.
13.65.
Point what?
86.65.
865. I think it should be that. I don't know where the 198 came from. I have no idea. So let's fix that. So it should be 13.865. Clearly the calculus is fine. I'm not exactly sure where the 198 came from. That's easily fixable. So why don't I just do this for now? We'll just say 13.865. And we'll just do that. Okay, so how about now? We good? Questions? Okay.
Where do you get the 100 from?
Yes, that's because the plane's going 300 and the car is going 200. So the net dx/dt, like the rate of change of the horizontal distance between them, would be the difference between the plane's speed and the car's speed. Make sense? You clearly can tell that the y is not changing, right?
Yeah.
But the x is changing. So if you just put 300 in for dx/dt, that would essentially mean that the car is sitting still and the plane's going.
Oh,
If you put 200 in there, that means that the plane somehow is sitting still and the car's going. But if the plane's going 300 and the car's going 200, the net rate, essentially, we're talking about kind of a water tank question, sort of, would be the difference between the two rates. Good question. Anna, what's up?
why did you plug in the 0.5 at this point in time?
Before I differentiated?
Yeah.
Why would I do that? Can anybody explain?
Because that 0.5 is constant, because it's always going to be the same distance between the cars.
Same vertical distance. Yep. So anything that's a constant, so think back to like the ladder questions, right? So the ladder is dropping down the side of the house or whatever. Remember how we always said x squared plus y squared equals 12 squared? It's because the length of the ladder not changing. And so anything that is constant, we can, and we really probably should, plug that in first. Yeah, great question. Anybody else? Number 1. All right, so number 2 was a L'Hopital question. You get infinity and infinity right off the bat, and then you get it again. And finally, in the end there, you get a constant, a 2 there, divided by something that's going to get gigantic. And so that means we're heading towards 0 for our final limit. And then you can see number 3 poking out there too. Number 3 was tough with some of the algebra once you got your derivative. And even if you did the product rule right, and even if you did the quotient rule right, there was some challenging algebra yet to be had. Bless you. Reese, question?
Could you change that second rule, or second term to make it a product rule, just with the,
Say it one more time.
make that second term product rule by just making it.
Sure, x times y to the negative 1, absolutely. Yep, you'd end up, of course, you'd end up with like a y to the negative 2 in there somewhere, so you'd want to maybe clear that out. Well, I guess you wouldn't even have to clear that out. You probably would just end up with a y to the negative 2 in your answer somewhere. So that would be fine. That would be fine. And I think that idea is not a terrible one. I mean, that's a very simplistic quotient rule, so if you decided to do a product rule there, I don't see really an advantage to either one, other than you picked one of them, so I would go with that one. So you guys have any questions on 2 or 3? Have you noticed I've done a ton of implicit differentiation questions over the semester? That's just because that's something that people usually need a lot of time to get really, really good at, and I think you're getting to that place where you're probably getting good at this, and this was probably a tougher one for sure, involving all the different details it did, but I don't know. What do y'all think? Questions, concerns, comments? Little detailed questions, what ifs? Anything at all? Just give you a little space here. Okay. Nobody's got their hand up. Nobody's saying anything. Okay. So let's do this. We're going to do a little work here in Unit 5. So if y'all would flip over to that. There we go. There we go. Okay, so do you guys remember from, gosh, it's been a while. I can't even say when. Do you guys remember this? Remember the boxes? So what we did before is we had a box. We opened it up. There was another box. We opened that up, and we finally got to the thing we wanted. So if I could sum up today in one action, it would be this. Just going to put them back together. Make sense? Okay. Obviously, there's some details to be had and some things to deal with. And we'll get there. Okay, so take a minute here. Take maybe 1 or 2 minutes. I want you to think about this. If you were presented with an antiderivative like that, let's just think for a minute, ponder some of the steps you might have to do to get to the finish line. It's x to the third minus 5 to the 200th times 3x squared dx. Just take a minute and think. what might be my first step, what might be the second step, something like that. And if you as you ponder that, if you start to get a little fearful, I would understand. Just think about those first steps. What in the world would you have to do? That 200, right? Seems like kind of a big deal. Okay, so take a minute, share, or pair up, I should say. Pair up with a classmate and look at what you, or at least discuss what you've been thinking about. Like, what are some of the things you'd need to do to be successful on this?
Oh, yeah. Can't forget that plus C.
Interesting. I just said interesting, that's all. Okay. Let me ask you a question. I don't know where you all went with this necessarily because I haven't seen everybody's paper. Did anybody see that 200 and think that they might need to multiply that out? You know, like x cubed minus 5 times itself 200 times? Anybody think about that? Remember, it's been a week, but maybe you remember this. When we were working on our antiderivatives prior to Thanksgiving, I made a comment about, and maybe you remember this, where if we see a fraction in an antiderivative, we are going to do our best to avoid that fraction. And then I made and sometimes we won't be able to avoid it, but we'll try. And then I made another comment that we kind of feel the same way about products. In fact, I think I made this comment. I said, over the course of our whole year together, you're going to learn exactly one way to deal with an integrand that's a product. You're going to learn one way. So you can clearly see this as a product, right? And so I made the suggestion that we should probably try to avoid products as well. So can I show you the wrong way to do this and explain why? So people get tempted to do this all the time. They'll look at this, they see that it's a product, but they'll treat it like it's a sum, and they'll just go with this. They'll say it's x cubed minus 5 to the 201 divided by 201 times, now hold on, times x cubed. Right, so what they did is they did some kind of a power rule there, and they did some other power rule there. Remember, antiderivatives are essentially just the reverse of the derivative. And so shouldn't I be able to take that answer, differentiate it, and get what I started with? So I should be able to just go ddx of all that. And this is where I first run into a pretty significant issue, because if I'm going to do the derivative of that, what am I going to have to use? The product rule, which is going to be blah, 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 plus blah, 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 right? And this is where I run into a serious issue, because my original integrand was not something plus something. It was something times something, wasn't it? And so if you've got a product as an integrand, to find the antiderivative, you can't just go antiderivative of first term times antiderivative of second term. And essentially the reasoning is the product rule will disprove you pretty much every single time. Does that make sense? So if you were to realize this and say, oh my gosh, I can't do this, and so I really, really don't want this integrand to be a product, what can I do? Maybe this is where you would say, well, what's the only way to take something that's not a product, or something that is a product, and turn it into something that's not a product? Like, how could I turn that into something that's not a product? Witchcraft? No. Come on. This is basic algebra. Wouldn't I need to take that x cubed minus 5 to the 200th, multiply it by itself 200 times, and after all that's done, then distribute 3x squared?
I mean, do it.
No, I'm not suggesting that this is the right way, but I'm saying if you wanted to take something that is a product like that and make it not a product, isn't that exactly what you'd need to do? So my hope is by getting you to think about this, you would say, oh my goodness, I don't want to do that simply from a time perspective. No one has that much time, myself included. Might there be a smarter way? So let me review. If you've got an integrand that's a product, you simply cannot do the antiderivative of the first factor times the antiderivative of the second factor. And the reason why you can't do it is it simply doesn't work, right? It's not the antiderivative. And multiplying the sucker out is just a non-starter because we don't have all week to do one question, right? So there's got to be a better way. Let's look at it. I do this a little bit uniquely. If you were to sit in on a different calculus class or just look this up on the internet, you're going to see probably one of the two ways that I'll show you. You might see the way that I show you two. I'm going to show you two ways. The reason I'm going to show you two ways is because I think one way is really quick, and if you get it, it can really help you be fast and accurate. The other way will always work, and it's a little bit slower, but there are going to be certain situations where you have to use the other way. So I'm going to teach you both. So the two ways are, number one, pattern recognition. And because you guys have done a lot of chain rules, I'm guessing you're probably going to be pretty good at pattern recognition. And then the other one is called change of variable. And this can also be called substitution, or sometimes I'll refer to it as U substitution. The letter U is not particularly important. It's just the letter that seems to show up a lot. So I thought I would help you guys a little bit with pattern recognition here today, and then later on this week and on into next semester, we'll look a little bit more at the change of variables. Okay, so pattern recognition. Can anybody tell me what that derivative is? ddx of f of g of x?
F prime times g of x plus g prime of x.
Is this not f prime times g of x?
F prime g of x.
Of g of x, right? What is he using to get there? He's using a chain rule, isn't he? Okay. So then, notice how the chain rule always yields a product, right? Isn't the chain rule going to give you something times something else? Okay. And that's key here, right? Because we're going to be looking at integrands that are products and maybe have elements of composite functions in there as well. The chain rule is going to be the key. So here's what I want you guys to think about. If I were to take what I just had right there, in fact, I'll write ddx, so rewrite the whole thing down here. If I were to take this, and if I were to do the antiderivative with respect to x of both sides, right, I'm maintaining balance in my equation. Let's think about what would happen on the left side. How does the antiderivative interact with the derivative? They just cancel each other out. And so the left side, that would be f of g of x equals, I'm going to leave the right side alone because this will kind of help us see our issue here. Notice how the left side is f of g of x. The right side is the antiderivative of f prime of g of x times g prime of x dx. So this is where people will often say, hey, I think I get part of this, but part of this I don't. They will look right here and they'll say, I think I understand why this prime seems to go away. They'll say, I get that the antiderivative of f prime of g of x would maybe be f of g of x, right? They'd maybe think, okay, I get that part. But then they'll look over here and they'll say, I don't understand where g prime of x is going. Because notice on the left side, essentially, doesn't it seem like that g prime just sort of disappeared? So I want to explain where it goes, because it does seemingly disappear. If you can understand where the g prime came from, maybe you'll understand where it went. So this is going to be a chain rule. I'm going to do the derivative to this box. You've seen this before. When I do the derivative of this box, isn't this f prime of g of x? When I take this out and open it, what's this? That's g prime. There's my dx. So if I'm doing an antiderivative of one of these products that's got a composite in it, wouldn't it be fair to say, if I'm going to reverse this, I just put this back in here? Doesn't the g prime just go back where it came from? It disappears back inside. So if you understand that the g prime came about as a result of a chain rule, well, wouldn't reversing the chain rule just make it go back where it came from? It's going to disappear back to the inside, back to the input. So that's kind of where it's going. One little note about this. This is really important for what we're going to be doing today and in coming days. If I've got the wrong g prime, if I've got the wrong derivative of the inside, for instance, if I started off with this and I said, hey, my g prime is that. I lost the Santa or something. My g prime is this, and I try to repackage this in here. It doesn't fit, right? And even then, if I were to try to jam it, I end up with this mess, right? So it's really important to understand that the g prime, sorry about that, Mark. It's really important to understand that the g prime has to be the correct g prime. And we're going to find some times where it's not, and we'll need to deal with that. That make sense? Hope that came through on the video. I was banging around with some boxes. The audio probably was not sufficient. Okay, so in order to help us with this started a long time ago. I created this character named Timmy, and it's not named after any one of my students. I have had a couple of Timmys over the years, and I just apologized to them and said, I don't know where I came up with that name. It just came to me one day. Timmy almost always has an issue, serious issue. Basically, Timmy doesn't have a clue how to do the chain rule most of the time. Sometimes he gets it right, but most of the time, Timmy completely messes this up, and this is my representation of Timmy, kind of looking a little clueless up there, I don't know what to do, and we need to help him out a lot. So I just want to remind you, we just saw this on the other screen, that the antiderivative of f prime of g of x times g prime of x dx will always equal f of g of x, with the one important note is that g prime has to be the correct g prime. Okay, so we're going to find a lot of times we're going to need to fix Timmy's issue. Sometimes we won't. A lot of times we will. So a lot of times he's going to have some major problems with the chain rule, getting that g prime to be the correct g prime. So I thought I'd run through a couple of these here with you. I probably use this technique probably about 98% of the time. The other 2% is when I got to use the other one. I like it because it's accurate for sure, but it's quick. And if I can spend 1 minute on something and get it right versus 3 minutes, that feels like a win to me. So let's take a look at some examples where Timmy might need some help. Okay, so here we go. When I have the antiderivative of a sum, do you guys remember that sometimes, and this is going to be one of those cases, it's going to be best to split it up into two separate antiderivatives? So I'm going to do that first. So I'm just going to say antiderivative of x squared plus 1 to the 100th times 2x dx, and then plus the other one here, 1 over 4x minus 9 dx. Okay, so remember this is pattern recognition. We want to look at the different elements in here and recognize what we need to do. So here are some of the hints you'll see. The biggest one probably is going to be, do you recognize that at least one of the elements in there is composite? Let's focus on that first one. Do you guys see any composite aspects to that first one? Yes? Okay, so x squared plus 1 to the 100th, clearly a function inside a function, right? So here's what you want to look at. Look at the inside, and you want to ask yourself, what is the derivative of the inside? So this is where you respond with, wow, that was uninspiring. 2x, right? And then you want to check and ask yourself, is the other factor a 2x? And you respond with?
Yes.
Yes. So this is going to be one of those rare cases where Timmy didn't mess anything up. Most of the time he does. He didn't mess this one up. So here's what I need to do. I need to recognize that in the process of reversing the chain rule here, this 2x is simply going to disappear back inside. Right? It's just going to go back where it came from. And the only thing that I really need to do the antiderivative of is the big box. So this would be x squared plus 1 to the 101st divided by 101. And again, this is a time where people will say, man, I'm so confused because where did the 2x go? Well, if you just recognize that this is a reversing of the chain rule, it's just going back where it came from, right? It came out as a result of the chain rule. It's going back in. Say again? Well, reversing the chain rule, yeah, it's going back to that input, right? It came from the input. It's going back into the input. You guys okay? Okay, here's the other one. The other one's a fraction. And do you guys see how this fraction is kind of an unavoidable fraction? Like when you first look at this, does anybody have any instincts on this? What do you think the result will be on this? Natural log, right? It is natural log. But in order for this to be a natural log, the derivative of the denominator has to be the numerator. So what's the derivative of the denominator? This is where you really need to engage here. It's 4, isn't it? You look up at the numerator and you say, oh my gosh, what happened, Timmy? You messed it up, right? The numerator should be a 4. It's not a 4. So this is actually something we can fix. So what I'll do is I'll go in and I'll say, you know what? Timmy, I got your back. Now the numerator is what it should be, right? But I am not allowed to do that, am I? I can't just go in and say, hey, 1, you just become a 4. Unless I also balance it out. So if I multiply the integrand by 4, what's the only way to balance out what I just did? How do you divide? How do you reverse or how do you counteract multiplication? Division. So check this out. If I multiply the inside by 4, I'm going to multiply the outside by 1/4. So effectively, what have I multiplied this integrand by? 1. I've changed the form, but I have not changed the value at all. I've changed the form into the form that I want. So the end result here would be plus 1/4 natural log absolute value of 4x minus 9. Finally, I get to my plus c. Now, if you ever have doubts about these, you look at it and you say, whoa, okay, I sort of kind of maybe get this, but I'm not sure if that's the right answer. What do? Do a derivative. Should get you back to where you started. Okay, let's do as many of these as we can. Let's kind of hopefully get some good rhythm here. Number 2. Do you see how number 2 is also a sum? So we'll split this one up. And this is where I'd like, now that you've seen one, maybe those that are catching on, I'd like to get some better input from you. Here is what this would look like. Let's focus on the first one. Do you all see how the first one is composite? So that means the chain rule needs to be correct. So look at the inside. What's the derivative of the inside? 5. What should the other factor in the integrand then be? It should be 5. But what is the other factor? It's a 1. So Timmy, once again, messed up. Yeah, we're gonna shake our heads at Timmy an awful lot. I'll just tell you that right now. So we can fix his issue though. It's not hard. He's off by a factor of 5. So I'd multiply the inside by 5, and I'd multiply the outside by 1/5. That's why it's super important that we split these types of integrands up. Because when you look at the other term, e to the 8x, again, you see it's composite, right? So what should the other factor be? Because isn't the derivative of 8x 8? Yeah, so the other factor should be 8. Yet the other factor is just a 1. So Timmy, once again, wake up, Timmy. The other factor should be an 8. We can fix it. If I multiply the inside by 8, I have to multiply the outside by 1/8. So that means my final answer would be 1/5 sine of 5x. Remember, once you get the chain rule correct, the only thing you do the antiderivative of would be the big box, like the outside function. And then what do you all think the second term would be?
1/8 e to the 8, 1/8 e to the 8x.
1/8. You said a lot of 8s and 1/8. I want to make sure I get this right.
E to the 8x. Yeah,
Okay.
that's what that makes sense.
So this is where, you're correct. This is where people get a little confused. They look at this 5 and this 8, and they say, well, where in the world did those go? Because they seemingly disappeared, like by magic. Can anybody explain what happened?
They went back into the box.
They just went back into the bigger box, right? They did kind of disappear. I mean, if I were to take these and put them back together, I mean, you could do this with dogs and cats and 2-year-olds. You can say, where'd the Santa Claus go? And they'll be like, I don't know. You guys know where it is. You can't see it. Can you see the Santa Claus? You can't see it, but you know exactly where it is, right? So you can't see the 8 anymore. You can't see the 5 anymore, but you know exactly where they are. They just went back to the inside. Okay, I think we have time for one more, perhaps. See what we got. I like them both. I'm going with number 3. You've seen all you need to see. This is just repetition at this point. So, for this first one, we need to do the split up thing. When I do the split up thing, are you guys in the mode of just automatically doing this? Like rewriting radicals, right? Okay. Plus, this over here would be cosecant squared of 10x dx. I hope you can see that you got a bunch of composites up there, and you have to split these up like I just did. You really have to do that. Okay, let's see how good you are. Let's see how good of a helper you are for Timmy. Timmy messed up on both of these. What factor should we multiply the inside by in the first term? Say again?
1/2.
No, not 1/2. We're not going to do our antiderivative yet. Look at the inside. The inside is x cubed plus 1. So if it's a correct chain rule, what should the other factor be? 3x squared. Do you see how Timmy does have the x squared in there? He's off by a factor of 3. Timmy, again. So if I multiply the inside by 3, how do I balance that out? 1/3 multiply the outside. Yep. Okay. Timmy messed up the other one too. Can anybody explain what you think the fix should be on the inside? Say again? 10. Because isn't the derivative of 10x 10? So this really is a composite. That needs to be a 10, which means we need to multiply the outside by 1/10. So we have fixed all of our chain rules. Timmy's errors have been dealt with. We're ready to find the antiderivative. So I think, Isabel, this is where you were trying to go. You were wanting to deal with this 1/2 right away. Well, now we are, right? Because isn't 1/2 the outside, like the big box? So for the first one, my antiderivative is going to be 1/3 times x cubed plus 1 to the 3/2, right? But then I have to divide by 3/2, which is the same thing as multiplying by what? 2/3. Plus 1/10. And what's the antiderivative of cosecant squared?
Negative cotangent.
There we go. So it really would be negative cotangent of 10x. We got our plus c. And you could simplify that a little bit. Obviously, you get 2/9 on the first one, and you could mess around with the second term a little bit. There you go. Anytime you want to check these, you just do a derivative, and you should end up with what you started with exactly. Yeah, so we'll keep working on these, but tomorrow we will do a Unit 4 test review. Hope you all have a wonderful rest of your day. Take care. Enjoy the sun.